We can do a warm-up problem. Find the integral from 0 to 2 of 3 square root 4 minus x squared minus 1 quantity squared dx. And you may use any of the following. The integral from 0 to b of 1 dx is b. Integral 0 to b of x dx is a half b squared. Integral from 0 to b of x squared dx is 1/3 b cubed. These are all things that we have proved using Riemann sums. We will have better ways to do that by the end of today. You have some options. What's the answer? Have people worked it out? Which one did you say? D. D? As in David? It's not the best answer. But did you say D as in David, perhaps? B. Yes, B. All right, 50 minus 6 pi. Now, what happens? Well, you sort of say to yourself, this doesn't look like something I can do right away. And that's a good instinct. Most integrals aren't things you can do right away. But you say, I have algebra. I remember those good days. So you square it, because you have something squared. A minus b squared. A squared. When you square the square root sign goes away. 2ab. So that's where the 6 comes from. 2 times 3 is 6. Don't forget this is a minus. And then b squared. Well, group 9 times 4 plus 1 is 37. Then you have your minus 9x squared and your minus 6 root 4 minus x squared. And you can break this up into 3 pieces. And 2 of these pieces, you can use the integral. Then there's this weird piece. And we talked about last time, geometry. We can use geometry. And so it's good to be able to say, I know certain shapes. Triangles, squares, oh my, and circles. So whenever you see something like square root a squared minus something squared, you should be like, looks like a circle. And so this is the circle of radius 2, but not all of it, just a quarter of it. And so you end up with 74 from the first part. You end up with, what does it end up being? Negative 24 from the second part, and 6 times pi from the last part. So 50 minus 6 pi. There we go. All right. Well, for today, what's our thought? Well, the greatest teacher failure is by Yoda. Although perhaps we should see if we can't channel our inner Yoda. The greatest teacher failure is. I'm not very good at channeling Yoda. At some point in your life, you come to the realization that the person who gave voice to Yoda also did Miss Piggy. It's the same person. And so once you know that, you start to say, I can believe it. So, all right. So why do I say this? Well, I think there's a lot of hesitancy on behalf of students. And it's kind of natural. It's not fun to fail. You could even say that it sucks to fail. Excuse my language. But, I shouldn't swear in front of students. But, we don't want to experience that. At the same time, how do we learn? How do we grow? We learn from mistakes. Sometimes we're lucky and we learn from other people's mistakes, but often we learn from our own. And so we have to learn to be willing to try, to be willing to stick our necks out. And yes, sometimes we'll win, that's great, and sometimes we'll lose, but even in losing, we can learn. Now, it's not that losing will automatically make you better, but what will happen is that when you make a mistake, you have a chance, a wonderful opportunity to say, what happened? Study, see where you made your mistake, and you'll say, I see what I did there. That was so silly of me. And I won't make that mistake again. You'll get a chance to make some new mistakes. And it's wonderful. It's wonderful. All right, so today. You probably figured out today is an important day just by the handout, because it seems extra thick today. They love this topic. You could even say that this topic is fundamental to the course. So, we're going to talk about the fundamental theorems of calculus. And there's 2 of them. But as always, you should focus on the fun part and not the mental part. So, we're going to have fun. And this is our chance to say, there's these 2 ideas. One, finding totals. The other, finding change. We want to tie them together. Okay, so the first variation says the following. Let's make a new function from an existing function. So the picture here is you have an f which depends on t. And now what you're going to do is you're going to find the total from starting at a and going out to x. And so we have this function, our total function. The punchline is, if we take the derivative of this new function, we get back the function we started with. So the derivative of the total is the change. All right. Another way to phrase it is, remember the derivative is, how is something changing? So the question is, how much is the total changing by right now? And the answer is, well, whatever the function you're trying to find the total of. And that's the answer. Now, the tool we're going to use is the mean value theorem. So we talked about this last time, so I'm writing it down for reference. If we have a continuous function, so technically this is for continuous functions, but that's not a big hurdle. We'll talk about that later on. If we have a continuous function from, let's say, a to some point b, and then there is some point in between a and b where the function is equal to the average. So the mean here, if you remember what the word mean came from, this is really an average. So the mean value theorem is about averages. So I have some point where I match the average of the function from a to b. All right, well, let's prove this. So, how do we take a derivative if we don't know what's going on? What do you do? If we want to take a derivative and we're not sure what to do, where do we go back to? The limit definition. All right, so we're taking the limit as h goes to 0, f of x plus h minus f of x over h. All right, that's just the definition, no surprises. And then we say, well, hold on. I know what f of x is. It's this total. So what's going on here? Well, what's going on, we can think of it as we're going from a to x. That's this total here. But then we have a second one, which goes from a to x plus h. So there's a slight gap here between these two. And so we'll just add some shading here. And we say, all right, if you take the integral from a to x plus h, subtract the integral from a to x, what are you going to have left? So take the big, subtract the little, what's left? That little strip there. So it's the integral from x to x plus h f of t dt. Yes? So this comes back to properties of definite integrals that we talked about last time. Now, we look at that expression and we start saying, that looks familiar. It's like we've seen that somewhere before. 1 over x plus h minus x, integral from x to x plus h f of t dt. Have we ever seen anything that looks like that? Anything at all? No? Are you sure? Let's look closer. I'm pretty sure that there's something that kind of looks like that. Oh, the mean value theorem, right. Oh, very convenient here, right? So here it's a to b, here it's x to x plus h. Same thing. So it's like, cool. So what does that say? Well, it says that there's some place in between x and x plus h, maybe it's, let's say it's here, so that this height is the average of the function between x and x plus h, which is not too surprising. Well, now we say, well, let h get small. C is between x and x plus h. So if these two are coming together and C is in the middle, where is C going to end up? It's going to end up at x. It's going to be squished like grapes. So you get f of x. And that's the argument. That's it. That's the fundamental theorem of calculus. So one of the things that this tells us is that all continuous functions have an antiderivative. Because you start with your function and you find this total. Now you're saying, cool. Any downsides to that? Well, that's in theory. In practice, most functions do not have a nice antiderivative. So be careful. Be careful. All right, any questions about this? We're going to go through and talk about variations in practice. And don't worry, there is a sequel coming. There is a part 2. All right. So, I've written down for reference, this is the way that's oftentimes the compressed notation. So the fundamental theorem of calculus can be written this way. The derivative of the integral from a to x of f of t dt is f of x. All right. Now, we're going to do some variations here. Suppose I take a derivative not from a to x, but from a to g of x, f of t dt. What would that look like? See a hand going up?
Be f of g of x.
F of g of x, huh? Okay, cool. Cool. Let me write some notes down. So you said f of g of x. So I'll write that down. Is that the answer? Is it really the answer? Let's think about what's going on here. So we called this function f of x, this the integral from a to x of f of t dt. So, and that's the idea, integral a to g of x of f of t dt. What would that match with in terms of capital F? It would be what? F of gx. See, like this says, whatever you plug in here, that goes upstairs. That's the rule. Well, here, what's being plugged in upstairs? G of x. So, running it backwards, that says that's where we're going to plug into f. Now, that's this expression here. We have a function in a function. Chain rule. Chain rule. It's the greatest rule. It's a chain rule. So, the derivative of the chain rule says take the derivative of the outside. This is the outside. Plug the inside in. So this is great. But is that all the chain rule says? Then you have to multiply by the derivative of the inside. So it's f of g of x times g prime of x. So it's chain rule. So the f, again, that's the derivative of the outside. Plug the inside in times by the derivative of the inside. All right. Cool. But let's suppose we want to go one more step. Suppose we want to go a function of x to a function of x, f of t dt. What would that look like? Look like what? All right, so let's think of what we can do. When we think about this, we say, well, when in doubt, try to reduce it down to something we can do. What's something that looks like this that we know how to do? What's above it, right? A to g of x. So let's say, well, this looks like a to g of x of f of t dt plus something else. Think of your properties of definite integrals. What can I match it with? It match with h of x up to a. Because I'm essentially gluing these at a. So if I go from for h of x up to a up to g of x, those match. Well, I don't like the a upstairs. I want to put it downstairs. How can you put it downstairs? Well, the answer is you put it downstairs. But it comes at a cost. If you flip it, what happens? You have to opposite sign, make it negative. Good. So this expression is equal to this expression. We haven't taken any derivatives yet. We just say these two are equivalent ways to write it. So if I want to take the derivative of this expression, it's the same as the derivative of that expression. Well, what does that become? Take the derivative of the first, and we get f of g of x times g prime of x minus, what's f of h of x, h prime of x. And this is the very much generalized form. And this will always work for any kind of bounds. All right, are we ready to try it? We've got our tools. This is very handy. They oftentimes like to throw interesting functions into bounds. So if you don't believe me, look in the handout. Okay. So, whoops. That page is trying to stick together. There we go. Let's find the following. We got a whole bunch of expressions here. And let's see how many we can get through. Okay, number one, we want to find the derivative of the integral from 10 to x of sine of t to the fourth e to the t dt. What do we get? What do we get? Does anybody have an answer? This is one we'll do together. Unless, would you like to do it yourself, and then we can come back together in a few minutes? I mean, that's fine with me. All right, then if we're going to do it together, all together now, what do we get? What is this 10 acting as? Oh yeah, you betcha, So it's a to x. What is this sine t to the fourth e to the t acting as? This is our f of t, right? So what's going to come out of this derivative? Someone said f of x. What is f of x? Sine of x to the fourth, e to the x. Everywhere where you see a t, put an x. Nice. And are we done with that one? Do we need a plus c? No, there's no derivatives in plus c. Psh. All right. Second one. The derivative of the integral from 3 to 7 of x squared dx. What will that be? This one's meant to be misleading in notation. So it's okay if it's like, this feels misleading in notation, Steve. Zero? That's a bold answer, and it's correct. Can you explain why it's 0?
Because we're evaluating from a number to a number. So when we do that, we're just going to get a number and taking the derivative of any constant is 0.
Yeah, so an integral from 3 to 7 of x squared dx is a number. It's a known quantity, or at least it could be a known quantity if you could figure it out. Then the derivative of a number is 0. Another way to put this is, do you see this x here? It's a symbol. We could change it, and it doesn't change the output of the integral. So what do you want to change it to? Anyone have a favorite number, symbol? What?
1.
Well, we can't use 1 because that represents the number 1. 0 represents the number 0. We need a symbol that can be a variable. Okay, we'll go with y. I know, you're probably thinking, why? If we change it from, instead of x's like x squared dx to like y squared dy, it's still the same integral in terms of the computation. But now, how many x's are showing up? No x's are showing up. And so what's the change with respect to x? Nothing, because there's no x dependence. All right, the third one. The derivative of the integral from x squared to x of tangent cubed of t dt. What do we have? So what's the first term? I heard a few quiet voices, but just want to make sure I heard them right. Tangent cubed of x. Now you could also, if you wanted to say it's tangent cubed of x times the derivative of x, which is 1. All right, what comes next?
Minus 2x tangent cubed of x squared.
All right, so minus, and I'm going to write it as tangent cubed of x squared times 2x, just to emphasize the chain rule. So first off, we plug, everywhere we see a t, we put an x. And then times by the root of x, which is 1. Then we're doing minus, because we subtract the lower 1. And everywhere we see a t now, we put x squared. So it becomes tangent cubed of x squared times the derivative of x squared, which is 2x. All right. Now, one more to go. What's the limit as x goes to 0 of 1 over x to the fourth times the integral from negative 1 to 5x squared minus 1 e to the t squared sine of t plus 1 dt? You're like, this is a crazy problem. You'd never ask this on a test. Except we did. This is from an old exam. All right, so let's think about this. There's another way to write this. This is the limit as x goes to 0 of the integral from -1 to 5x squared minus 1 e to the t squared sine of t plus 1 dt over x to the fourth. When in doubt, or I shouldn't even say when in doubt, when you're faced with the limit, what's the first thing you should do? Plug it in. And maybe you don't even have to do anything. So let's plug in. When you plug in 0, let's do the denominator because that looks friendlier. When you plug in 0 downstairs, what do you get? 0. When you plug in 0 upstairs, what do you get? Probably 0. Okay, probably 0. Can we make it a definitely 0? Why would it be 0? You'd have integral from -1 to -1 of something. But what happens if you have an integral that starts and stops at the same place? You get 0. So it is a definitely 0. All right, so we have 0 over 0, which means more work. More work. Okay. And people are like, aha, le hôpital. Yes, yes, we are definitely going with le hôpital. Okay, so this is doing our friend le hôpital. Still limit, we still haven't gone out of there. Derivative of the downstairs. 4x cubed. All right, the derivative of the upstairs. No, come on, not everybody at once. Take your turns. Okay, so the good news is we have an a to a function of x. So we're going to be plugging in everywhere we see a t, we put in that 5x squared minus 1. Yes? So e to the 5x squared minus 1 squared sine 5x squared minus 1 plus 1, also known as 5x squared. Anything else? Right, chain rule, 10x. Now, the question is, how many more derivatives do you want to take? Because we can do it with as few as 0. Or as many as 3. It depends on what mood you're in. Now, someone's like, go for 3, Steve. We don't need trees. Cut them all down. We'll fill up all the paper. Maybe we'll go with 0. We can cancel an x, upstairs and downstairs. Now, the exponential is fine. We can live with it. The 10 is fine. We can live with that. It's this sign part. We have to think about that. Cancel a 2 here. There's a 5 there. So, do we have any nice facts? Well, let me first rewrite what we actually have. So we have a limit as x goes to 0. Upstairs, we have that 5 e to the 5x minus 1 quantity squared. Downstairs, we have 2. These are all things that we're okay with. And then we have things we're not okay with. The reason I say we're not okay with these things is that they're currently making zeros. We don't like zeros. We want non-zeros. So there's a times here. Now, do we remember anything about limits and sign? Limit as blah goes to 0, sine of blah over blah, testing your blah memory, is 1. We almost have sine of blah over blah. Almost, not quite. How do we get there? We put a 5. Well, if we put a 5 there, we'll put a 5 upstairs. What will this part go to? 1. Now, what does this part go to? We have 25. We have an over 2. And e to what power? Plug in x equals 0. Negative 1 squared, which is positive 1. 25 halves e. Just what you thought. As soon as you saw 0 over 0, you're probably like, this has got to be 25 halves e. That's what it always is, right? No. It's always more work, more work. But that's all right. We don't mind. All right, so there we go. Whew, that was a good workout. Any questions? Okay. Well, let's do another problem. So given that the derivative of the integral from x squared to pi of t cubed f of t dt is 16x to the 17, find f of t. And that's for t greater than or equal to 0. What can we do? What can we do? Perhaps we should focus on this side for a second because it says take a derivative. Can we take a derivative of that integral? Notice the function is only downstairs, not upstairs. So it's going to be, we can think of it as 0 minus. So if you think about plugging in the upstairs, because you could plug the upstairs in, right? Plug the pi into t cubed, plug the pi into f. But then what would you multiply by? The derivative of pi, which is 0. So a constant will lead to a 0 term. Okay, now we're doing the bottom. We have an x squared. We're thinking everywhere you see t, put in x squared. What does that give you? So x squared cubed, which becomes x to the 6, and f of x squared. Good. Are we done? Just when we thought we were done, this problem pulls us back in. What else do you need? 2x. Chain rule. Don't forget the chain rule. It's a great rule. Okay, now that's just the left-hand side. We haven't done anything to the right-hand side, so that is what it is. Now what can we do? Sure. Let's try to get this by itself. So we have an x to the 6 and a 2x. We can move those terms over. And then we have a minus we can move over. So if we move all that stuff over, it will get a minus. What will our constant term be? Don't forget about the 2. And that we move by dividing. So it's 8. Right, we divide the 2 across. What will be our power? Tally your x's. Sorry, what?
The 10th.
To the 10th. Where do you get 10th from?
You subtract the first x from the 2x, and then you subtract the 6 x's, or you get the 6 x's from that.
Yeah. So there's 6 x's plus 1 more x makes x to the 7th. You divide x to the 17th divided by x to the 7th is x to the 10th. Okay. Is this our answer? And why not? This is f of x squared. We want f of t. Well, what are we going to do? we're going to change the name. We say, congratulations, x squared, you're now called t. All right, so we have to come over here. What are we going to call this? X to the 10th. X to the 10th, what's the way to write that? X squared to the 5th, t to the 5th. So f of t, our final answer, minus 8, t to the 5th. And you might say, oh, wait, but that only works if we can write x squared as t. What about negative values of t? To which we respond, we don't care about those. Because there was a little assumption made. T is greater than or equal to 0. All right. Okay, so that was fundamental theorem of calculus part 1. We need part 2. So, what does part 2 say? Still fun. So now it says, suppose I have a function, little f of x, and I have another function f prime of x that equals little f of x. So in particular, what we're really saying here is that capital F of x is the antiderivative of little f of x. So this is what this statement is. If I have an antiderivative of little f of x, and I want to integrate a to b of little f of x dx, I can use the antiderivative. But the really cool thing is, I only have to look and say, what's happening to that antiderivative at the endpoints? So I plug in f, capital F at b, subtract, plug in capital F at a. So that says, hey, if you're looking for integrals, definite integrals, if you can find antiderivatives, life is good. Because now you plug in. All right, so this really gets to the fundamental, like, oh, integrals, definite integrals, finding totals, and finding antiderivatives, which comes from understanding change, really are nicely connected. So how does this work? Well, what we start with by saying is that the fundamental theorem of calculus number 1, it tells us that if I'm finding a total, which is what the integral from some arbitrary number c up to x of f of t dt is, that's an antiderivative. Now, I'm emphasizing un. Why do I emphasize un? How many antiderivatives are there? Well, there's many. But how do they relate? Plus a constant. So this antiderivative that I found may not be the exact same as the total, but at most it's off by some constant. That's the punchline. So the antiderivative is acting like the total function within a constant. Now, from there, we're almost done. Because we say, all right, if I want the integral from a to b of f of x dx, we break it up into two integrals so that we match what we have here. So this c is very deliberately matching these two c's, which in turn match each other. We flip the second integral, like we did a few minutes ago, and then we say, aha, this first integral, moving the d across, that's the antiderivative at b minus that constant. The second integral, antiderivative at a minus that constant. The constants cancel. And so the great thing is, which antiderivative do we need to find? What's the answer? Any antiderivative. As soon as we find one, we're fine. So when we're doing the problems that involve definite integrals, when we look for antiderivatives here, we don't care about the plus c. Because we can choose c. So we choose it to be 0. So our procedure is, we say, look, start with your integral, find your antiderivative, and then you do an evaluation. So this is important notation to get used to. So this says evaluate f of x between, and you take the high value, plug it in, subtract the low value, plug it in. So f of b minus f of a. So that's the theory. Now, there are, of course, challenges. Not every function has a nice antiderivative, so we may not always be able to make that work. Be ready to use other approaches. We've already mentioned some: geometry, symmetry. How do computers do it? Well, if it has an antiderivative, computers are pretty good at finding antiderivatives. I don't know if they're as good as humans, but they're pretty good. And if it can't, there are numerical methods. And you might say, oh, that sounds cool. Where can I learn those? Next semester. We're going to talk about that. Good times. Okay, so fundamental theorem of calculus part 2. We can use antiderivatives to find definite integrals. All right. We have time to do a couple of examples. Any questions before we run through examples? Cool. All right, so we have 4 antiderivatives. We can do these. Our 4 integrals. So again, our mantra is channel your antiderivative. Is there an antiderivative of 2x minus 3? What is it? Someone said x squared and x squared minus 3x. So you find an antiderivative, and then you plug in 0 and 2. When you plug in 2, what do you get? 4 minus 6, which is negative 2. When you plug in 0, you get 0. So the answer is negative 2. Are we okay with it being negative? It's okay for definite integrals to be negative, because things have signs. You have to be careful not to get too attached to the idea of integrals are areas. If you were to sketch this, what you have is it looks something like this. And you say, well, there's some part below the axis, and that's a negative contribution, and there's parts above the axis, which is a positive contribution. And so you're okay with having negatives as definite integrals in some cases. There are some cases where you don't want it, where you're saying, I have a definite interpretation. And like if you say, I'm trying to find something which I know is an area which should be positive, and you got a negative, you're in trouble. All right. Our next problem, find the integral from 0 to pi of sine of theta. Now, I should note, we can already do the first integral with geometry. This one, hopeless with geometry. But now we have better tools. Do we have an antiderivative of sine? Negative cosine. So this would be negative cosine theta evaluated 0 to pi. So negative cosine pi, subtract negative cosine 0. What's cosine pi? Negative 1. What's cosine of 0? Positive 1. So you're like this, there's a lot of negative signs, so let's unravel. Minus minus makes plus, minus minus makes plus. All together we end up with 2. Well, that's kind of nice. Okay, our next one. Integral from negative 1 to 1 of 1 over t squared plus 1. Do we have a nice antiderivative of 1 over t squared plus 1? Or if you like, 1 over 1 plus t squared. Channel your inner Steve. What problem would Steve want to show as an example? What function would there be? Arctangent. Yeah! We can integrate that. That's on our list. It's a great entry. That's arctangent of t. By the way, notice here we had x, here we had theta, here we have t. It's always the same principles. -1 to 1. Arctangent of 1, subtract arctangent of -1. Do we know what the arctangent of 1 is? Pi force. It's the angle that when you plug into tangent would give us 1. Arctangent of -1? Negative pi force. Put them all together, we get pi halves. So probably you weren't expecting pi to show up. So it's kind of interesting. An interesting one. All right. Our last problem, the integral from -1 to 1 of 1 over x squared dx. Well, we make this calculus friendly. X to -2. Integral of x to -2. X to what power? X to -1, and you put a negative in front, right? -1 over x. Evaluate from -1 to +1. When you plug in +1, what comes out? Subtract. When you plug in -1, what comes out? So we end up with -2. Okay, now this, you're probably like, cool, 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 we're done, right? That's clearly the answer, right? Right? But something suspicious happened here on the way to the answer. We went from -1 to +1. We were finding this. What do you notice about this? It's all positive. We should end up with a positive number. How did we end up with -2? What's going on? Did we break math? A little bit. So what's the issue here? Well, the issue here is you have something blowing up. So we can't use fundamental theorem of calculus directly, not continuous. There is this underlying assumption of continuity. Now, you can do piecewise continuous, but why can't we do this particular integral? Well, the issue is it involves infinity. And you're probably like, oh man, I really want to do integrals which involve infinity. Is there any way I can find out how to handle integrals which involve infinity? And you do it in Calc 2. Oh my gosh, you're probably like, oh, I gotta take Calc 2 now. It has all the cool stuff. All right, thank you.